one of the work that we do in the micro end milling realm here is look at diamond coating, very thin, conformal and continuous diamond coatings. The main reason for going thin is to not blunt the edge radius or whatever features we put on the tools. We grow our own diamond coatings in here. The reason they're nanocrystalline is we're trying to make 100, 200 nanometer thick coatings. We need to be able to grow small crystals with that. We have a small chemical vapor deposition reactor. It's just a very small system for research. We generally grow on one tool at a time. However, this process, as you may or may not know, is completely scalable. They're commercially available 16-inch diameter chambers where one could put hundreds of certainly micro tools at a time and coat them. You flow in methane, excess hydrogen, just 4 to 6% methane hydrogen in here. Tungsten filaments, just like the old light bulbs here, we get them to about 2,000 degrees Celsius to dissociate those gases. All right. And the radiation from them heat the substrate, in this case a micro end mill, and then the gases come down under the right pressure, gas mixture conditions. When they hit the surface, the hot surface, chemical reactions occur, and ultimately what we're looking for are diamond bonds forming. And so literally it is a, atom by atom in that sense process of synthesizing or growing this diamond film on the coating. So we do this in-house with our collaborators. This project is in collaboration with Dr. Karpik at Penn, University of Pennsylvania, and Dr. Suman at Argonne National Labs. One of the great things that we've found in micro milling is the low friction and the low adhesion of materials to diamond. Why? I mean, diamond bonds are very strong. Unless you get a dangling bond out there, they don't want to attach to other things. That's why you get low friction and low adhesion. And this has great benefit as we shrink down. We get more surface area for the volume we're trying to cut, and so it helps a lot. Even with something as easily machinable otherwise as aluminum, we can see sometimes significant force reductions when we're micro end milling with the diamond coatings because there's less adhesion. And also a big thing, the chips don't stick in the flutes. I mean, not even just talking the cutting zone, but evacuating material up the flutes of the micro end mill.
So in here we work on metal matrix nanocomposites. So we're taking lightweight aluminum and magnesium alloys and pure metals and then adding nano silicon carbide or other ceramics into them to create a strong matrix or a strong composite material. And recently we found that we can double the strength of the matrix material with just a 1% volume addition of the ceramic nanoparticles. And when you compare that to conventional metal matrix composites where you put in, say, 20% of 10 micron or so size silicon carbide pieces, we get better strength enhancement, but we also don't pay a lot of the penalties that you typically see with metal matrix composites. Normally when you put 20% silicon carbide into an aluminum, you make your material that was once very ductile, very brittle. You also make it very difficult to machine. With these small additions of nanoparticles, we can enhance the strength even more so than the conventional composites without having to pay any ductility or machinability penalties. When you make these materials, the real trick is getting the nanoparticles broken up and well dispersed into your material. Due to the high surface to volume ratio of the particles and the high associated interfacial energy that you create as you disperse the particles, the nanoparticles really like to agglomerate and they really don't want to break up and disperse into your material. To overcome these problems inherent with nanocomposites, we use an ultrasonic technique to break up the clusters. The ultrasonic energy creates cavitation events in the melt. These break up the clusters. It also creates a streaming or sort of a bulk flow of the material, and that then serves to distribute these now broken up nanoparticles into the melt. And then we then can cast it. A lot of nanocomposite processes are either powder-based or severe plastic deformation based, where you're very limited in the geometries you can create. And as far as the powder metallurgy goes, it's also very expensive and time consuming. By using a liquid process, we still have our geometric flexibility and also can do it quite rapidly. So there's a tip that goes on here that actually extends down and dips into the melt. That then creates the cavitation and streaming in the melt that brings in the particles as well as breaking up the clusters of the particles.
So that's what disperses the nano.
Right, that's what disperses the nano ceramic phase, yeah.